Hello, my name is Jack Fitton, and I'm going to be doing the Test 3 Wrapper problem review video for problem number 3 from Test 3. So problem number 3 is a emotional EMF problem with a bar moving downwards with velocity v towards a resistor with resistance R, and there is a B field pointing out of the page right above the bar. So part A asks for the magnetic force on the mobile electrons in the center of the bar due to the motion of the bar. So with that, you can set up an equation for F mag that is going to equal the charge times the velocity of the bar crossed with the magnetic field. And so in order to do this V cross B, you're going to have to set up the direction of these direction of this velocity in the B field. And so you can do that by looking at those two directions on the diagram. So the velocity is moving downwards, which would be defined as negative y. So we can change this to we can change this equation to negative e, since that is the charge, to v negative y crossed with b, which is pointing out of the page, which would be the positive z direction. And so you can then pull out v and b, and then just leave y, and you can also pull out the negative, which would cancel this out, cross z. And when you do this, you're going to get y cross z would give you a positive x. So the final answer will be the charge E times velocity times the magnetic field in the x direction for F mag, force due to the magnetic field. Part B asks us to draw an arrow in the bar to indicate the direction of the conventional current through it, and also indicate the rough distribution of positive and negative charges around the bar using positive and negative symbols. So I will quickly draw out this diagram of the bar moving downwards with velocity, with a B field outside of it with the bars and the resistor. So in order to determine the conventional current with this bar, we're going to have to look at the magnetic force and which way it pushes the electron. So if you were to think about the F magnetic force that we just calculated in A, you can see that it's in the x direction. So if you think about it, the magnetic force will then push all of the electrons into that same direction, which would be to the right. So these electrons are negatively charged, so when we push them to the right side, it's going to create a negative charge on the right side of the bar. Hence, the other side will be positive. And if you think about directional current will flow from this negative side to the positive side. So the current will be this direction in the counterclockwise of the loop. Or of the loop. And then so negative will be on the right and positive will be on the left. So now that we have those labeled, we can look at part C, which asks for the magnitude of the voltage along the length of the bar. With this, we can set up an equation from our formula sheet of change in voltage equals the magnitude of the electric field times the distance of the bar, or the distance between the two bars that the middle bar is sliding down. So that would give us this first equation. And then in order to define E, we can set up another equation of the force of the electric field equaling the force of the magnetic field, because you can set the magnitudes equal to each other. And then the electron force is defined as charge times magnitude of electric field, which equals you can define magnetic force again as the charge times V cross B. Then you just cancel out these, and E will equal VB. Because it's cross, you can go ahead and assume the sign 90, which would make this just VB. So now you can plug this in, and changing V is going to equal drift speed times magnetic field times the width, or in this case you can see the distance right here. And then we can move on then to part D, which will ask for the power used by the resistor. So you can easily set up this equation, power, which will equal P, variable P, which then equals the equation given on the formula sheet of the change in voltage squared over the resistance. And if you think about it, we've already solved for this change in voltage in the part C, so we can just easily plug this in right here. So P will equal VBW squared over R. And that's an easy equation and an easy plug-in for power of the resistor. And this R is the resistance of that resistor as defined in the problem. And lastly, for part E, it'll ask for the steady state speed of the bar in terms of the other parameters given in the problem, as well as fundamental constants. So this is an interesting concept, as we can now use the gravitational force and set that equal to the magnetic force. Because if you look at this magnetic field pointing out of the page, if you think about if you use right-hand rule, where this is the direction of the current pointing this way, this will be the current, and then the perpendicular to that will be the B field, which will be out, and then your thumb will point in the direction of the force. So the magnetic force due to this B field will be pointing up, because B field points out of the page and current goes to the left. So that magnetic force is supposed to cancel out or work against the gravitational force, and so these can be set equal to each other. So F mag, so the magnitude of that magnetic force is going to equal the magnitude of the gravitational force. And we now have to define these in some way. So F mag is going to equal an equation of current times this width again times the B field, which then just equals change in V over R, which you can plug in for a current times WB. And then, knowing change in V is still defined already in part C, you can plug that in again, which is going to equal VBW over R times WB, which equals W squared B squared V over R. And then for F gravitational, it's the basic equation we already know of the mass of the bar times the gravitational constant G. And M is defined already in the problem, so we can use it. So we set these equal to each other. And just isolate V or solve for V. So V will equal mg times resistance over width squared times the magnetic field squared. And that should be your final velocity in terms of given variables and constants. And so that is each part of the problem. And this is an emotional EMF problem. It was a hard problem that I struggled with, so I thought I'd go over and let you guys know how to solve for each answer. Thank you.